Day 24, LRU cache. It's one of the most important questions, and it's asked very frequently in many programming interviews. So let's see how we will implement it. First, let's understand the LeetCode problem, which is problem number 146. In general, the API that the client wants is to access the keys. They may not necessarily want to put keys. This put is something which can be internally used by the cache, but the problem in LeetCode asks you to implement a class LRU cache, which will have a capacity. So maximum that many elements can fit into that cache, LRU cache, and you need to implement two methods. One is get. So user will just get the key. If it's in the cache, it will return from the cache. If it's not, it will return you the key, the value, and also it will put that key into the cache so that next time you access this key, it's accessed from cache. And you also need to implement put method. So here you need to pass key and value, the user of this code, and your task is to put this value under this key. And LRU means least recently used. And generally the name of caches comes from their eviction policy. Every cache has some capacity and they are not as big as the memory, but they are smaller than that. So they have to keep some capacity, and there need to be some eviction policy on what basis you will pop the elements. So here the eviction policy is least recently used. So you have 10 keys that have been accessed. Now you have 10 capacity only, and now user accesses a key which is not present here. So you need to insert this latest key also in the cache, but you have support for 10 keys. So what will you evict? Which key will you remove? So you will remove the least recently used. That is the key that was accessed 10 time steps ago. So whatever is the last or least recently used item in the cache, it may not be exactly 10 time steps, because let's say this first key is accessed again and again and again. So this will itself be accessed 10 times ago. But whatever is the 10th element, least among these that are present in the cache. So for example, let's run through this example. Initially, the cache is empty. And for our case, let's say the capacity is 2. So first time we put 1. So key is 1, value is 1. So we have 1. Now our size becomes, or count becomes 1. Then we put 2. So size becomes 2. Now we want to get 1. So 1 is present here. So it should return 1. So it returns 1. And 1 is the latest. Earlier 2 was the latest key. Since we put it, this was the last key or the most recent key. Now when we access 1, 1 is the most recent key. So 1 is here, 2 is here. We will keep the most recent in the beginning. Now we want to put 3, but our capacity is 2. Size is already 2. So we have to remove one of them. So this is recent. This side is recent. So we will remove 2 and put 3 here. Now 3 is the recent one. Now we want to get 2, but 2 is not there in the cache. Only a space for 2. So we return -1. So all the key values will be positive. This has been said in the problem statement, so that you can return something when the key is not found. So you will return -1 in that case. Now you want to put 4. So you put 4 in the beginning. So this is the most recent, and 1 is removed. Then you get 1, 1 is not there, so you return -1. And get 3, so returns 3, get 4, returns 4. So that's it. So let's see how we will implement it. So there is a standard algorithm for this. You have to implement both of these in order one time, that is constant time. So so how you can get key? In order to get, you have to return it in constant time. So naturally something comes to your mind that I will keep a map where I will have key and some value, because map allows you, hash map allows you to get or access key in constant time. So you will have map, but how will you maintain the ordering? That is, you have to remove the least recently used. This map will not have ordering, although some languages like Java has some high-end version of hash map called linked hash map, which also remembers the order in which elements were inserted. So if you iterate the elements, the order is guaranteed. It will be the same order it was inserted. On the other hand, hash map does not guarantee the order of access, simple hash map. Similarly, in Python, we have ordered dict, which is very similar to this linked hash map. So it's different from normal dictionary. But in C++, we have the normal unordered map, normal hash map. So we will additionally use a linked list data structure, or which will act like a queue. So you keep inserting in one end and you remove from other end, which will denote the least recently used. And we will use one hash map. And Java and Python internally implements this. So we will see the code of all of the three languages. So let's see how we will do it in C++ first. Or let's forget about the language. Even these would internally be doing something like this. So we have a linked list or a list and a hash map. So we put 1. So we put 1 here. Let's delete it. There is no node. We create a node. We put 1 here. And let's say this side is the most recent. So 1 is the most recent. Then we put 2. So 2 will be inserted here. 2 is most recent. And capacity is 2. Now I want to access 1. We also put here 1 and 2. This will also have always this many elements. If we remove from here, we also remove from the map, so that there is a consistency between linked list and map. And what do we store as value? Let's say I want to insert 3. So I want to insert 3. Then I have to remove this. So I will remove the last, and I will also remove the key from here. That is simple. So removing is trivial. You can access the last element of this list and remove that, and also remove it from the map. So that will be done in order on 1 when you want to remove something. And remove will be used during put, not during get, because during get you don't need to remove anything. So during put, removing is easy, and putting is also easy. You put in the beginning. But when you are accessing get some key, then getting it from the map is order 1, fine. But that key may be in the middle of the list, somewhere in the middle. Here I am taking example of 2. That is not a good example. So let's say this key is here. So we got the key in the map, but how do we bring this key to the front? because searching in list will take order and time if you do it like this. So now you understand why both are important, map and linked list. Linked list because you need the ordering, you need to remember the ordering. Eviction policies to evict the least recently used element. So that can be done in list or queue or similar data structure. But then problem with list is that accessing would be order and time. On the other hand, if you look at map, accessing would be order one, but ordering information is lost here. We don't remember the ordering. So we need both of these. So how we will pair them? So we want to access a key, let's say it's 5. It's somewhere in the middle. So we see in the map and we get it in the map and we can return it. Now our second task is to move it to the front because it was used very recently. So we need to somehow store the value and also the position where this element is in the list. So you keep track of not just value, but also position in list, both the things. So key is one integer, value is a pair of the value corresponding to this key and the position in list. And this is required. So you get the key, you return the value to the user, you also get the position, you go directly to that position in the list and you bring it forward. So in C++, we will be storing the iterator, the list iterator. And in Java and Python, we will not need to keep track of these ourselves. We will be using linked hash map and ordered dict. So let's begin programming. First in C++. So we have to first implement the constructor. So let's keep the private member variables. We will need capacity. Let's call it capacity. Then the list. We can call it keys. And then unordered map. First, the key is integer and the value is a pair of integer, which will denote the actual value that we put using this function. And the second will denote the position in list where that key exists. So for this, we will use the iterator of same type, whatever is our container for keys. And let's call it map. We can also call it cache. Then in constructor, we can member initializer list we can use. Or it's equal, you can write it here also, capacity equal to capacity. Now let's implement the get. So we will only return a value when it exists in the map or the list. If it doesn't, we will return -1. So if map dot find key not equal to map dot end. So this is the case when key is found. So when the key is found in the map or the list, what we will do, before returning, we need to move that key to the beginning of list. And also this map is holding the position of that key in the list. So we need to update this also. So let's do keys dot push. So we have to remove this from the list first, then only we will push in the beginning. So let's remove it. Keys dot erase. And what is the position that we want to erase? From the map, get key. This will return this, the value, which is a pair. And now the position will be the second element of that pair. Dot second. So we will remove that. Now we have to put it back in the front. So keys dot push front. So now this part is done. So we have removed from that position and put to the beginning of this list. Now we will update the same in map. And then we return map key, and first is the actual value. Oh, I have wrongly put this here. So if the key was found, then we did these things, moved the key to the beginning, then updated the map. If it does not find the key, we will return -1. So we have implemented get. Let's remove this, it's causing confusion. Okay, let's implement the put now. So the same check. If we are putting something, if that already exists, we will move it to the front. If it does not exist, we will insert in the beginning. So let's do that. This part should remain same. So we remove it, we move it to the beginning, and then map key equal to the value and keys dot begin. Else, if it's a new key, we need to check the capacity. In this case, capacity does not matter because it was already present. We are just moving it to the beginning. But if we are inserting a new element, a new key, that is the key that was not existing, we need a capacity check. If keys dot size this greater than check is not required, you can do with equality, but let's add it, it does not harm, or let's remove it. It's greater than capacity or equal to capacity, then we have to remove it, remove one element. So front of this keys denote the recent, back denotes the least recent. So if size is equal to capacity, we remove one least recently used. Now irrespective of that, so we have decreased the capacity by 1 here beforehand. And if it was already less than capacity, then it will not enter this code and it will simply insert in the beginning. And we are done. So let's try it out. It works for this case and looks to be a good case. Let's go ahead and submit. So our solution is accepted. Now we will write this in Java, and here we will use linked hash map. So we will not need this list. It will keep track of the ordering itself. You can also implement it using the same way. You just use the hash map instead of linked hash map. That would be a good exercise. But here I will use linked hash map. So let's keep some private variables, which will be the capacity. And then linked hash map. Now we will add the constructor. So capacity equal to capacity and map equal to new. Constructor is done. Let's implement the get. The same way, if map dot contains key, then get the value. Remove it. Why remove it? Because this map is not simple map. It remembers the order in which it was inserted. So first we found it somewhere in the middle. Then when we remove it, it's removed. And we have to put it back. So when we will just put it back, it will be inserted in the front. That is as it will remember that this key is the most recent one. So it will automatically take care of everything. You just need to remove it and insert it back. So the ordering will be automatically maintained. So remove it and then map.put key value and return the value that we fetched from this. And if it's not there, return -1. So this takes care of everything. Now let's implement the put. So if map.contains key, if it contains key, then we have to remove it from there and put it in the beginning, the same way what we did in C++. Only thing is that here it's much easier due to absence of list. So map.remove key. And if it's not there in the map, then it's even simpler. You just put it in the beginning. And also check the capacity. So if it contains the key already, no capacity check, just remove it. And in the end, we will put it back. So I am not putting it here because this will be common to both the cases. We have to put it back in the end. So for clarity, let me write it here, then we will remove it. Map.put key value. If the key is present, we remove it, put it back. It will be removed from some middle position and put in the beginning. That case is done. What will be the second case? If it's not present in the map, if it's not present in the map, then we are inserting a new element. So capacity check is required. So if capacity is equal to capacity, or okay, this capacity, and this we will get from the size, map.size. So we have to remove the first key that was inserted. The way to get is map.keyset. It will return you the set of keys and you have to use the iterator dot next. This will give you the iterator to the first key that was inserted, so you have to remove that, and you have to also put it back, and you will notice that this part was common, so we put it outside, and this is done. So let's try it. Key value map dot put line number 14. It's val. Now it works. So let's submit. So this solution is also accepted in Java. Now finally we will implement it in Python. So we will init with two things: capacity, same as Java. And this solution is much more similar to Java than C++ because we will be using ordered dict, which also remembers the order in which keys were inserted. If key in self dot map, exactly same as Java in fact, value equal to self dot map dot pop. So this will pop and also return the value, and then we will push it back. Else return -1. Next we will implement put. Or else if length of this is equal to capacity, then we have to remove the first key. And by default it will be true, last equal to true, where it will follow last in first out. So you have to write false here. So this will mean FIFO. So if you don't put this default value, default it will be true. So when you pop an item from this map, this ordered dictionary, it will pop the last item, the recently item that was pushed. So if you write it false, then it will pop the first item that was pushed. So it will follow FIFO, and we are using FIFO, first in, first out. So the one that was inserted in the beginning will be popped out here. So let's try it out. And it works in Python. So let's submit. And the solution is accepted in Python as well.